in between. So the dense activity is the same. It doesn't change. So that must be some type of clock sync. The transmitter and the receiver don't know how long, let's say, like a high or a low is. So if you don't know how long it is, you could misinterpret something that was supposed to be low for two bits as 1 bit if you don't have some type of sync. So you're going to see stuff like this to see a sync. So it figures out, it syncs off the transmitter, and it's like, okay, the time period for a bit is this long because I've received so many patterns that are sent across, and then I can start processing the data in between. And that's the data. So we're going to take a look at this a little bit closer. And so you have a clock sync. After a clock sync, you're going to have to tell the other device some way of knowing, like, oh, get ready. This is going to be the data that's really important. You can't just start flipping bits because it might be part of the clock sync. So that's why there's that part in the beginning that has about 5 ones. That's telling the other side, hey, get ready. I'm going to send some data. And if you'll notice at the end, it sends about 5 zeros, and then that lets the other side know, okay, I'm done. You can go back to try to listen to a clock sync again. Here's the same thing in a logic analyzer. In the logic analyzer, it's going to tell you what the bits are. Don't be fooled that think that this parallax scope can do this. This is me inside of like paint.net clicking on there and typing zeros and ones so I can write it down. They don't do this for you. A logic analyzer will do that for you. It still doesn't know what the period is, so that's why there's the big sections of, let's say at the beginning, it says 1B for 1 binary, and it doesn't know that it's 5 separate bits. But the good thing is that you can take, for various of these tools, you can take the data and dump it into like a comma delimited file, and then you could do some kind of, if you wanted to, you could do some kind of heuristics on it and determine protocols that way. Or you can figure out the clock cycle and then run a script through it, and it'll dump it out for you. So here's the complete protocol, including what was decided was the header and the footer. These are the 3 buttons that come on this device. Page up and page down, that's to forward and, to go back and go forward on the slides. And hide, you push that button and it turns the screen black. So this data is obviously going to be some kind of header and some kind of footer. It doesn't affect our determining what the serial number or the key codes are. So we get rid of that. Now we do the most rudimentary of, I don't even want to say cryptanalysis because it's not cryptanalysis, but you just match what's the same and what is different. So these are common across all packets, so this is probably the serial number. And these are different, so these are probably the key codes. And this is the protocol. It's going to have a header. It's going to have part of the serial. It's going to have data, a little bit of data, some more serial, data, and then a footer. So what kind of attacks can we do against this? Well, we can do passive attacks, sniffing. We can get maybe some types of authentication data. Really, that only matters in keyboards. Trying to figure out if someone's clicking on stuff on a mouse is not going to get you anywhere. Trying to see if someone's using a presenter, you're probably in the room watching the presentation, so you know what they're doing. But you'll get the authentication data. You'll get the serial number, which you'll need in order to inject traffic. As far as active attacks, there's always denial of service, and then there's what everyone wants is execution of arbitrary commands on the target system. So how do we do this? We bring our own microcontroller. We're not going to use their microcontroller. It would be ideal if we could just reprogram their microcontroller and not have to wire anything up. But the problem is it's one-time programmable, so we can't even reprogram it. One-time programmable chips are way cheaper than flash chips. Flash chips are just used for development, and then once you have your code worked out to the point that you want, then you do a run on one-time programmable chips. And you can't even read them anyways because the security fuse is blown. And at this point, we already know the protocol, so there isn't anything that we need from that device. So RF is hard. Designing RF is hard. There are people that specialize in doing RF design, and they're great at it. I'm not going to be great at RF design. I don't care about RF design. I just want to send data. We don't need to even know about RF design. We don't need to have a scanner. We take over the OEM equipment. We take over the dongle, and we take over the transmitter. That already has a working receiver and has a working transmitter. So we're going to use those against the target. And what happens is, if you start injecting data into the transmit chip, and then you're receiving from the receiver chip, you've basically created like a metaphor of a network socket. You're putting data in on one side, and it comes out the same on the other side. So this is how we're going to sniff at the chip level. All we do is we're going to either cut the trace or the pin or the connection between the receiver chip and the microcontroller. There might be a way to put the chip into high impedance, maybe. I don't know. I just cut the trace. So in this picture here, the metal can on the left-hand side, that's going to be the crystal. Right above that, you'll see that there's a wire soldered onto one of the pins of the chip. And I have all this electrical tape on it because that's my protection from it ripping out. Because you're soldering these little tiny things. So I usually use electrical tape around something to secure it down. Especially when you have these big floppy connectors. These clips, sometimes it can flip over and then it'll pull your connection off if it's not soldered properly. So this is how we start sniffing the data. And this is what we really want, is we want to send data. We want to inject at the chip level. So we're going to cut the connection between their microcontroller and the transmitter chip. This is a little fuzzy, but the wire that is coming straight out it cut the pin, and it connected via which is when you have like a dual layer board, just top and bottom, and you need to pass something across a path that's already been crossed. You can't cross it. So what you do is you run some copper, and then you make a hole and has copper inside of it, and then that connects to the other side, and you start passing back and forth. Those are great places to tap. They have a coating on it to protect it from corrosion or whatever, so you just take an X-Acto knife, kind of scrape that stuff off, and then you have a great location to solder a wire on there. It's a hole, and it makes a good connection. The two wires coming off the top, I'll come back to later, but that's coming off the EEPROM, and we'll be able. I'll show how you're able to sniff traffic between the EEPROM and the microcontroller. So, which is good for different things, but we want to. There's a lot of data going across between these chips, and it might be useful to see what they're doing. So we have to do passive attacks because we need authentication data. Like I said, from keyboards, we might be able to get passwords or other sensitive data. Mouse data, not so useful. The type of active attack that we would do on a device depends on what hit type. The hit type limits the kind of data that is being passed up. So there's basically two types, keyboards and mice. A presenter is counted as a keyboard. So if we're able to inject complete keyboard commands, this is what I'm going to send. I'm going to send the Windows key plus R. And that's going to pop up on their box. Then I could open IE to a machine that I control. I could run a command shell. Then I could echo data to a BAT file or some other type of scripting. You could use like Windows scripting or what have you. And then you have some kind of logic. So you could check for certain things. You could check IP addresses. You could try connections. You could do different. You have a program basically, and then you would execute the batch file. Active mouse attacks. Well, there's going to be two types of mouse attacks. One is you can see the target. You can see the screen. You can watch the cursor moving along. And then there's going to be blind attacks, where you're just going to try to guess where to move the mouse to and start clicking to try to get some kind of execution or something. So one is we're able to see the screen, and the other one is we're blind. This is how, for either of those, how we're going to try to execute commands. Microsoft has accessibility, and we have accessibility for our attacker. This is a virtual keyboard. If we can figure out the layout, we can type commands. Every time you open this accessibility thing, it always goes to the absolute center of the screen. Even if I've moved it around, I tried, by default it goes there, and then I was like, oh, I wonder if you used it and you close it somewhere else, is it going to open it up at the last location, or is it going to open it up at the original location? It always opens it up in the center. So now you have kind of a target of where you want to try to direct your mouse movement. So blind attacks, you have no visual feedback. You can try to make an educated guess. You can maybe kind of know where the start button is going to be. It's going to be, you can move all the way to the bottom. Maybe try to move a little bit up. Click the start button and try to get to the run dialog, or try to get to the virtual keyboard. To really do this, you're going to have some kind of scripting language to be able to send this data. You're not going to be able to do this manually. So the problem with being blind is, how do you know if something works? You need some kind of feedback. So what I would do is you control a web server. You have a Trojan on there. You're tailing the logs while you're doing this attack. And if you see a connection coming from that box, you know you're successful. If you wait a while and there's no connection, then readjust your algorithm and try again, and keep trying again. And there's going to be tons of things opened up on this desktop, but whatever, doesn't matter. So let's take a look at the toolkit. What are some of the things I used to do this, and what are some things you can use to do this? So microcontrollers. I started programming microcontrollers a long time ago because I wanted to reverse engineer the original PlayStation mod chips. The stealth chip came out, and I was like, damn it, I can't play games anymore. People are checking for the standard chip, and the stealth chip is doing something different. So I started programming microcontrollers, reverse engineered it, and that's how I taught myself how to program these things. Originally, I started with PICs, and they served me well, and I was at Kansas.